Okay, Nath. Yes, sir. It's now fine.
Okay,
Your
thank
voice
you
is
very
also
much.
clear.
Yeah, thank you very much for inviting me. And I hope
Okay.
that though it is a bit late, now people must be feeling hungry. But then, since you are at safe place, you can grab something and continue your brunch, lunch, whatever it is, and hope that you will be enjoying this presentation. Okay,
Okay.
so
Okay, sir.
my plan, uh, okay, so my plan of talk would be basics to some recent applications of underwater processing as well as water assisted processing. So those people who are already working in this area, some of the slides you may find that those are a bit basics. You have to kindly excuse me for that. So the plan is that what are the special properties of the laser beam which makes the lasers very important in industry, particularly in manufacturing industry for material processing applications. And since we are dealing with the various materials, so we must understand what is the basic mechanism of interaction of laser beam. And it has been seen that it has got very strong dependence on the laser power density or intensity, which is expressed as watt per centimeter square. That is the watt per unit area of the surface, what is the power. Then also it has been seen that how the material and laser beam interacts, it depends on the laser pulse duration. Whether we are using a CW laser or pulse laser, and in pulse laser, we have got nowadays available from millisecond, microsecond, nanosecond, picosecond, and femtosecond lasers. And particularly when we are using very short duration laser pulse, then the interaction mechanism becomes very different than the relatively longer laser pulses. Then we will discuss a little bit that what are the attributes, what are the importance or advantages of water assisted and underwater laser processing. Then we'll go through various applications of water assisted and underwater laser processing modalities, namely cutting, drilling, surface hardening, welding, grooving, paint stripping, shock pinning, nanoparticle production. And then with that, we'll conclude. Okay. The laser has become a tool of unprecedented precision and power. And because of that, it has become an invaluable tool for material processing application in manufacturing industry. The unique properties of the laser beam, many people would be knowing that it is coherent and it is monochromatic. And in the coherent property, the spatial coherent property gives the laser beam the property of very low beam divergence. That is, it doesn't spread much while it is traveling. You can get very high power, you can get very short duration pulses, and you get lasers of very different wavelengths ranging from infrared to ultraviolet. Now, this is a basic slides which shows that how the beam divergence affects the laser material processing. So if you see a laser whose beam diameter is W naught is the radius, and wavelength is lambda, and the beam quality factor is m square, and this m square value for Gaussian beam intensity is 1, then in that case, the half divergence angle is given by m square lambda by pi w naught. What is the significance of this? The significance of this that when we have got such laser beam and we try to focus with the help of a lens of focal length f, then the spot diameter here, what we generated is given by diameter is 2f into half beam divergence, where the f is the focal length of the lens. And if you put the typical values, the smallest spot diameter you can generate is of the order of the wavelength of the laser. Now the lasers which are available, excimer lasers, having the wavelength in the range of 0.2 micron. So one can get 0.2 micron diameter here. When you have got Nd:YAG laser, which is around 1 micron, then the diameter of the spot here will be 1 micron. And if you have got the CO2 laser, then it will be, which operates at around 10 micron wavelength. The diameter at the focal length will be, minimum diameter will be around 10 micron. So depending upon the laser wavelength and the beam quality, you can have very small spot diameter. And this focusability is very important for micro machining applications. Then the high power, you have got nowadays available laser, milliwatt. The pointer we use for using for presentation is in the range of 0.5 milliwatt. Then you have got the lasers ranging up to 10 kilowatt or more, tens of kilowatt. These are available in the commercially. When you use pulse laser, you can get pulse laser in the kilowatt to terawatt power level, and the pulse energy could be up to hundreds of joule energy in single pulse. And once you have got such high power laser and focus with the help of a lens, you can generate focal spot diameter practically in the range of 10 to 100 micron minimum spot size. And that can yield you the power density at the focal spot in the range of 10 to about 3 watt per centimeter square to 10 to about 14 watt per centimeter square. There is no other energy source which can generate such high power densities. As I mentioned, that lasers are available from continuous wave mode till different pulse durations. Shortest pulse duration practically generated and commercially available are in the range of around 10 femtosecond, that is 10 into 10 to the power minus 15 second. Lasers are available of different wavelength ranging from ultraviolet lasers like excimer lasers. Then you have got the large number of varieties of lasers up to mid wavelength. And the most important lasers which are used for material processing applications where you require reasonably high power and pulse energy. So you have got the excimer lasers, you have got the Nd:YAG glass laser operating at around 1.06. Then you have got the fiber laser in the same range. Then you have got the titanium sapphire laser, which are operating in femtosecond laser, and the CO2 laser. So CO2 laser, Nd:YAG laser, fiber laser, titanium sapphire lasers, and excimer lasers are the very important lasers for industrial applications. When you focus the laser beam, depending upon the power density, you can realize various effect on a material. If you have got the laser power density in the range of kilowatt per centimeter square, relatively low, then you just heat the material, and by heating, you can realize laser surface hardening and metal forming, where we don't allow the surface to be melted. If you go for high laser powers in the range of 10 to 5 watt per centimeter square, you can do the melting. So you can use for laser surface remelting, you can use for cutting, you can use for conduction welding, as well as what is called surface alloying, etc. When you go for slightly more power density, where the melt material can start evaporating, then the vapor pressure generated can create a keyhole. And through this keyhole, you can realize the deep penetration welding as well as the drilling. When you go even further high power densities in the range of 10 to 7 watt and more, then you can generate this vapor which is coming out. It can form plasma. And when the plasma absorbs the laser radiation, it becomes very, temperature goes very high. So pressure also increases. It generates a lot of shock wave. And this shock wave can generate shock wave hardening, which is known as a laser pinning. So by controlling the laser power density in this intensity, in this axis, y-axis, and laser interaction time, ranging from seconds here at the right side to 10 to the minus 14 second, you can realize all those processing applications like transformation, hardening, forming, cladding, alloying, cutting, welding, drilling, shock pinning, phase explosion, micro machining, all these things you can realize by this method. Now, how the laser beam interacts. In order to understand the laser beam interaction and appreciate its dependence on the laser intensity and pulse duration, let us see that what happens when the laser beam, which is basically an electromagnetic wave, which is incident on a material, and the material, if you consider metal, in that we have got a lot of free electrons. So these free electrons will be forced by this oscillating electric field of the laser beam, and they will start oscillating. And when they are oscillating, they are going to collide with others. And while they are colliding with other electrons, they are going to share their energy, and thereby the gas electron system temperature will increase. And this increase takes place in the time scale of around femtosecond time scale. And then these hot electrons, which are heated up now to several hundreds of Kelvin, thousands of Kelvin temperature, they are going to collide with slightly heavy ions, and these heavy ions are also slowly going to get energy from these electrons, and thereby they will start also share the energy of the electron, and thereby the entire system is going to get heated up. And this takes time of the order of around picosecond time scale or tens of picosecond time scale. So if you see the ultra fast laser operating in sub picosecond laser, then only the electron temperature is going to get heated up, and that time the ion temperature will be very less, because that the ion will not be able to thermalize with the electron within the femtosecond time scale. But when you so how the material which is going to get heated up by this is going to how it is going to remove the material. So the removal process in case of material femtosecond laser is through the phase explosion, Coulomb explosion, or direct vaporization. And of nanosecond and longer pulse, the material is going to get removed by thermal effect like the melting, vaporization, and ablation. Okay. Why it has got hanged up? Okay, so now how the like absorption is dependent on the material characteristics. The material characteristics on which the laser absorption depends is the refractive index of a material. We know that the refractive index of glass, which is a dielectric material in which we do not have free electron, the refractive index of glass is around 1.5. But when you consider the metal, where there is a lot of free electron, then the refractive index is complex, and it has got the real part and imaginary part. And depending upon this refractive index, reflectivity is given by this expression, and the absorptivity is nothing but 1 minus R, the reflectivity and transmittivity. In case of metal, which are opaque, the transmission is 0, so you get absorptivity in the material, which is equal to 1 minus R. So absorptivity depends on the complex refractive index of the material. And on this also depends on the absorption or attenuation coefficient. And this alpha is the characteristics of the laser and material characteristics, which is given by 4 pi k by lambda, where k is the imaginary part of the component of the complex refractive index. Usually, and inverse of this is tells me that how quickly the laser energy is going to get absorbed within the material. So it is known as the attenuation length. Sometimes it is also called as an optical skin depth. In metal, the K value is usually large because there is a lot of free electrons available. Because of that, the reflectivity R tends to become almost 90% or 100%, near 100%. And absorptivity 1 minus R becomes very, very less. And there the refractive, this attenuation length is also very small in the range of nanometer range. So what does it mean? It means that whenever the laser beam is incident, most of the laser power is getting reflected from the surface. Very small amount is getting absorbed in the surface, and this absorption takes place within a very, very small depth in the range of around 10 nanometer. So basically, we can assume that the laser power is getting absorbed on the top surface, and heat is going to penetrate inside the material, and thereby through heat conduction, the material is going to get heated up. When we go to very high power density, in the above discussions, we said that okay, this absorption is going to take place in materials where free electrons are available. But if you consider the glass or ceramic material, where we do not have the free electrons, then there is a lot of noise is coming. Yeah. Okay, so when we have got the dielectric material. Hello.
Okay.
Can you mute yourself while you are calling on phone?
ಅವ್ರು ಬಂದ್ಮೇಲೆ ಕಾಲ್ ಮಾಡಿಸ್ತೀನಿ ಬಿಡಿ. ಅವರು ಹೊರಗಡೆ ಹೋಗಿದ್ದಾರೆ, ಅವ್ರು ಬಂದ್ಮೇಲೆ ಕಾಲ್ ಮಾಡಿಸ್ತೀನಿ ಎಂದೆ.
Please mute yourself.
ನಿಮ್ಮ ಹೆಸರೇನಂದ್ರೆ?
Ankur.
Okay, ಮಾಡಿಸ್ತೀನಿ.
Ankur, somebody is talking over telephone. Please mute him.
Okay, so when we have got the material ceramic glass which do not have free electrons like metals, so how they absorb the laser radiation and how can we do the processing? So there comes the effect of high power. So when you have got very high power lasers which can generate power density on the surface in the range of 10 to the power 10 to 10 to the power 14 watt per centimeter square, correspondingly the electric field of this electromagnetic wave will be very high, and this will be in the range of around 250 megavolt per centimeter. And under these conditions, because of certain tunneling ionization effect under the intense electric field, some of the electrons of the bound electrons are going to get ionized and they will become free. There is another method, another mechanism happens when you have got very high laser power densities of this order. That time at one point there are large number of photons available, and therefore there is a certain finite probability that at a simultaneously there will be large number of photons are going to get absorbed, and therefore though the photon of each individual photon energy is less, but multiple photons will be able to bridge the energy gap and cause the ionization of this. And once a few electrons are generated, then by avalanche process in this high electric field, they further get accelerated and collide with other neutral atoms, and they ionize, and thereby a large number of electrons and ions are produced, forming a plasma. And once this plasma is formed, then it is going to electrons in the plasma, which are now free, can absorb the radiation and form the plasma. And from this plasma, the heat is going to now conduct into the material, thereby even the dielectric material which do not have the free electrons, they can absorb the laser energy. Here, the effect of nanosecond, femtosecond laser pulse effect has been shown. So when you have got the nanosecond laser pulse, basically the effects are thermal, that is the material is going to get melted, vaporized, and plasma is going to form if the intensity is very high. But if you have got very short duration pulse, then what happens? The electron systems get heated up in that duration, and they slowly in tens of picosecond time scale share their energy with the ions and lattice, and thereby they also get heated up. And these are all happening in femtosecond time scale. There is no time for material to undergo thermodynamic melting, and some amount of material which has got now heated up and which has got very high kinetic energy, they will just leave the material, or which we call like ablation or vaporization without melting. That type of thing can happen. So if you see the effect of nanosecond and femtosecond pulses. If you see the microsecond and nanosecond pulse, you see that lot of recast material of melt materials are there. But when you go to picosecond laser pulse and shorter, then you find that you don't have those type of effect of molten material. How the processing takes place. So as I mentioned, the laser beam gets absorbed on the top surface, and here the entire energy is getting absorbed and heat is conducted into the material. So one can find out how the surface as well as the material is going to get heated up along the direction of jet, that is the depth, can be found out by solving the one-dimension heat conduction equation. Though it can be done numerically to get the temperature distribution in time and space, but one can get the approximate solution by this set of equation. And this equation is dependent on what is the laser power density absorbed, thermal conductivity, kappa is the thermal diffusivity, and an error function whose nature is nearly exponential but slightly different, and its values are given like this. So from this, one can find out for a given pulse duration how the surface rise is going to take place, how it is going to cool down. Along the depth also, you can find out how the temperature distribution will be taking place in time. But when we consider the ultra short laser pulse, that time we know that electrons are only getting heated up. So we have got the electron heat conduction equation, and they are going to share their energy slowly with the ions. And this is the equation which is through which the ions are going to get heated up. So if you want to find out and the temperature rise of electron and ion and material removal, it becomes a very complex process. So people have tried to utilize the empirical relations taking from the informations from the experiment. So one can find out that there will be certain threshold of the laser intensity, laser fluence, up to which the material is going to get ablated. So now if you have got the intensity or fluence F0 incident on the surface, so one can find out that what is the threshold depth jet threshold up to which the material is going to get ablated. So that can be found out from this expression, and jet threshold is that depth where the intensity has reduced to threshold value. So from this equation, if you take the log of that, you can find out what is the depth up to which the material is going to get ablated. Here, our assumption is that the laser intensity laser is going to get heated up, is absorbed at the surface, and up to a depth governed by the optical skin depth or attenuation length. But when we consider the very high intensities, that time we found that there is a certain amount of hot electrons they cause diffusion inside the material, and this process is also very fast. Therefore, instead of optical attenuation length, here the depth is governed by what is called the electron diffusion length. So the expressions remains the same. Only thing is that we have got a different type of now the threshold for high intensity ablation compared to low intensity ablation. So based on these experimental results, people have tried to theoretically model and find out for a given laser fluence what is the depth up to which material is going to get ablated. However, when we consider the normal laser cutting, drilling, etc., where the process is reasonably fast, not like femtosecond laser, but still fast, where the heat diffusion losses are very small and one can neglect, then one can use the lumped energy or power balance equations, which are given by here. This is the energy absorbed, and this is the amount of the amount of material which is going to get evaporated through vaporization. So this is the basic energy balance equations. And when we are talking about the cutting, where the laser beam is moved per second with a velocity v or distance v per second, there you can use the energy power balance equations like this to determine how the laser how the temperature of the material is increasing, etc. You can find out from this. Okay. And based on all these effects, one has tried to find out that how the for a given laser energy, how the ablation per in gram, that depends. And this line is showing the line of lumped energy balance equations, okay, based on the previous equations which I mentioned. And this is for the nanosecond and microsecond laser pulse, which is where the losses are very minimal. And here it is for femtosecond laser, where the phenomena are very, very different. So people have tried to get the information from the experimental results and try to model. And as I discussed earlier, those are the three different models you can use and find out. So exploiting these effects, people have tried to get thermal processing, cutting, drilling, welding, surface hardening, rapid manufacturing, that is the additive manufacturing, laser forming, etc. And there are certain non-thermal effect where, like in a dielectric material, in a transparent glass, inside the material, you are able to generate the features. This is the laser shock pinning. And this is the very advanced concepts of two photon polymerizations through which you can generate nanofabrications. So this is the entire building, the main building of our IIT complex. And this is the 7-story building, has been made in less than a millimeter dimensions. This is of the order of around 500 micron, seen under scanning electron microscope. And you can see with the almost 10 nanometer resolution, you can build by two photon polarization effect. Now, why there is a need for underwater processing? So this need came from interest that there are a lot of nuclear power stations where many of the components which are flooded with water, okay? And once the reactors are running, they become, many parts becomes radioactive. And if due to lapse of time, because of the stress corrosion, cracks are generated, you need to repair them. Sometimes you have to cut apart the things and then take it out and then rejoin with the new components. And also the burnt fuel, which are taken out from the reactor, in order to allow them to cool in terms of radiation, they are put under in water tank around 30 to 40 feet beneath water, so that the radioactivity, they get absorbed in the water. Now, you need to dismantle these materials to take out the burnt fuel and do the processing and for the storage of the waste material. Now, how to do this cutting of these materials? So that and that also underwater. So these are the technical challenges drove the people to find out the new methods, new technologies based on lasers as well, to do the processing underwater. So how the laser beam, when they propagate in water, how they get absorbed. So if you see the CO2 laser gets readily absorbed in water. It has got very high absorption coefficient. But compared to that, this is the logarithmic graph. Nd:YAG laser and fiber laser, diode lasers, whose wavelength is in this range, they have got relatively low absorption. Second harmonic Nd:YAG laser has got relatively very low absorption. So one can use directly inside the laser, inside water, Nd:YAG laser, fiber laser, second harmonic of fiber laser, Nd:YAG laser, to do the processing. CO2 laser has got limited applications, but as I go along, I will tell you that how this has been exploited for use. In IIT Kharagpur, we have also tried to find out how the absorption of the fiber laser takes place when we focus the laser beam, because when the laser intensity at the focal point is very high, there are certain nonlinear effect takes place and the water gets heated up. So we have tried to find out how along the temperature rise, how the absorption coefficient that goes on reducing. Now, what are the attributes? What are the advantages of laser underwater processing? So there are lasers like Nd:YAG laser, fiber lasers, which has got very little absorption, better laser beam focusing. You get, because of the refractive index of water more than air, you get a smaller focal spot. Efficient cooling by water, surrounding water. Laser beam could be guided through the water jet. Improved material removal by water jet because of high shearing force compared to gas jet, and it is used for cutting and other material removal processes. Efficient material debris ejection by water vapor bubble cavitation effect. Better laser processing quality because of the effective removal of debris. Intense plasma produced when we are using CO2 laser, and this has been also exploited in many applications. And enhanced plasma shockwave pressure due to water confinement. This is exploited in laser shock pinning. This will just describe when we describe about the laser shock pinning. And reduced atmospheric pollution by waste gases and aerosols. Okay, because now underwater, when we are doing, the debris or fumes coming out will be relatively less. There are some drawbacks. Some laser power loss in water takes place. Reflection, scattering losses at the interface and by debris could take place. Possibility of corrosion of laser processed workpiece could take place. Sophisticated and costly water laser processing system compared to gas assisted system. There are different ways in which underwater processing has been done. Here, the laser beam has been put and along with a high pressure oxygen or air pressure, so that here where the laser beam is falling, a dry condition is created. Here, by putting a very high pressure gas jet, you have made apparently a dry atmospheric conditions. So in these two cases, you have got the dry conditions created by the high pressure gas. And here, along with the laser beam, you are getting the water also, and we are putting and creating the dry conditions and doing the weld processing. And here, it is inside the water, directly it is going through the water, okay? And here you can see that the water layer is just put on the workpiece and laser beam is impinged on this, okay? So these are the different ways through which it has been done. So in IIT Kharagpur also, we have tried to develop water assisted and water assisted underwater cutting, as well as normal conventional gas jet assisted cutting and processing, and try to compare the effect of all these processes. Okay, here I will just try to demonstrate how it works. Let me see that whether it works here or not. Okay, you can see this is the normal gas assisted processing, where you can see that there is a lot of debris are created and noise and plumes are created. Uh-oh. Here it is the water jet assisted cutting. So this is the water is coming and it is removing the molten material.
Any difficulty, sir?
Hello.
Yeah.
Any difficulty?
Ekinath sir, is there any problem?
Yes, slide shifting was a little problem. Let me see. Okay, see, this is underwater slide. Let me see. Yeah, it is underwater gas assisted. So you can see that how lot of aerosols are created and they are passing through the water. So the bubbles and these are. And compared to this, when you consider this is the gas assisted. Now we are showing you the water assisted underwater cutting. And you will find that how calm and very low debris and those things are created with water jet assisted. So water is coming along with the laser beam and this is submerged in water. So everything is inside water.
Hello.
Okay.
Ashish sir, sorry to
Yes.
interrupt you. Sir, sorry to interrupt you, but your slide is not visible, sir.
Is it not visible now?
No, sir, not visible.
Oh, let me then again do the sharing. Okay.
Hello. Ashish sir.
Hello.
Hello.
Are you,
Ashish sir,
I'm
are you with
trying
us?
to- Yes. Are you able to hear? No.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. We can hear you.
Okay. Are you able to see the slide or no?
No, sir, not
No,
right
sir.
now.
Okay. Let me share it again. Ah,
Yes, sir. We can see your slides now, sir.
okay. Ah, I'm trying to expand it. Okay. Is it visible?
Yes, sir. It is visible.
Okay. So I hope that you had been able to see this slide in play mode.
Yes, sir.
So it is a
Yes, sir. Yes, sir.
water.
Yes, sir. It is running.
Okay, this is water assisted underwater cutting. Again, some problem came.
Might be the reason that bandwidth might be low. So
Low.
it is not
Okay.
able to take video.
Okay, I will go for the rest of the things.
Slide, sir.
Are you able to see the slides now? No.
No, sir. Not right now.
Oh, again it got disconnected. Okay. Are you able to see this?
Yes, sir. We can see that. Sir.
Okay, so now I'm not going to show any video. So this is
Okay,
the
sir.
underwater cutting for decommissioning of nuclear reactor components. So as I told you, so most of the time when the CO2 lasers, which gets readily absorbed in water, those were available in late 90s. So that time, by creating a local dry cavity with the help of a high pressure air or oxygen atmosphere, directly the laser beam used to be incident on the workpiece, kept underwater and realize the cutting. And so this was being used in RRCAT Indore for Indian nuclear program. These developments were being done. And this was done, this is reported in Japan, how they are cutting even up to 100 millimeter thick blocks underwater by creating dry atmosphere. So here you can see the top curve, which is reasonably very small, and this is the bottom one. This is from the side. So from 80 to 100 millimeter material from the side, you can see that how the cutting has been realized. Sometimes in early 2000, one interesting development was done when the high-powered fiber laser and NDR lasers were developed, and here through a very fine water jet whose dimension is in the range of around 50 to 100 micron, the laser beam is guided through this, and then it is allowed to fall on the workpiece to do the cutting. So since the refractive index of water is 1.3 more than air, whose refractive index is 1, so at a proper incident angle, when the laser beam is focused, then it can be guided like a waveguide, and then it can be carried without much loss. So there you can see, so this was being developed, and this was being used for cutting many thin materials, slicing thin materials to create very good quality of cutting. So here you can see that how the laser beam is guided through the water jet, and then this is the laser beam focused. This is the water jet which is coming, and from here the laser beam is guided and it is going to cut. So the main advantage of this will be that water is going to cause cooling. It is going to cause very efficient melt expulsion, and you can have long focal distance, because usually the focal point is going to be limited here after the lens, but if it is focused, then it is just going to maintain the same focal dimension along the fiber water jet, okay, till it is incident on the surface. So here it shows that how the good good quality of microjet processing can be realized in silicon wafer slicing or creating the nozzle for injection nozzle for the petrol engines. And the other is the stent cutting. Okay, one can use the thin steel or tantalum sheet to cut, or tube to finely cut, and without any burr or any microstructural or heat affected zone in the tube. Okay, and then we in IIT Kharagpur, we developed underwater water assisted cutting, and we could also create very good quality of cutting by this method, which we developed with using our high power fiber laser. Okay. Now, when the CO2 laser was being used, and this has been used to process the glasses. Now, the glass absorbs the CO2 laser beam, and also it gets CO2 laser beam gets absorbed in water. So, in order to process the glass inside the water, high power lasers have been used. And when the high power laser focused CO2 laser is propagating, it gets absorbed in water, and the water gets vaporized, and the water vapor, when it is coming out, it produces a keyhole. And then with this, the laser beam is penetrating in and then reaches on the glass surface. On the glass surface also, the CO2 laser gets very readily absorbed, and then with that you can do the processing. So compared to the air, where it generates a lot of thermal cracks when you are doing the laser cutting. In case of water, underwater, with the help of a CO2 laser, you can generate very good quality of cutting without any cracks. Here, the alumina ceramic has been cut in air. You get lot of thermal stresses and the fracture. But when you do inside water, because of the cooling effect, you can do the cutting without any cracks or and good quality of cutting you can do. Here, the laser drilling has been shown. So in one of the experiments, they have tried to see what is the mechanism. So the mechanism in laser drilling in air is actually the melting, vaporization, ablations. But here it has been seen that in addition to these effects, you have got a lot of liquid jet induced impacts, which tries to also remove the material and realize the cutting. So the process becomes much more efficient. Here, with the help of femtosecond laser, they have tried to do the, in presence of water spray, the what is called the micro holes drilling. So this one is without water jet spray. Here with water spray, you can get very good quality of hole drill, micro hole drills. So here the femtosecond laser of 790 nanometer has been used to do the micro drilling of silicon with water spray assisted. Similarly, with the femtosecond laser, the scribing has been done, grooving in silicon and steel. So you can see that when you do in air, this is the quality you get. When you do with the water jet assisted, you get very good quality. So the water vapor which is generated because of the high intensity laser, they are going to remove all the debris and melt recast. There will be no melt recast and you get very good quality of material removal done. Here in IIT Kharagpur also we did with the CW laser and laser operating at 1 kilohertz modulated power laser, and we could see that with respect to the air, where we get lot of recast and melting when you are using high pressure water jet assisted grooving, you get very good quality of grooving done on silicon wafer. So you can get very straight wall and clean without any melt material, recast material left on the surface. You can get with the laser. This shows the underwater laser surface hardening. So when you use the underwater in laser surface hardening, you depend on the fast cooling in the bulk material. But inside the water, when you use, then the cooling effect becomes much more rapid, and therefore the micro hardness which we can generate is much higher compared to what you can generate in air. So these two graphs shows that this is in air micro hardness and this is inside water. Though the depth reduces because there is a certain amount of absorption of laser power inside in the air, in the water. Therefore, depth reduces, but the magnitude of the micro hardness that increases. This is the direct underwater laser welding. Up to few millimeter inside water, you can directly do the welding and get very good quality of keyhole welding. But if you go beyond 3 millimeter, beyond 1 or 2 millimeter, then you find that the laser beam gets absorbed and creates a lot of plasma here, plume here. So the laser power cannot reach up to the surface if the water depth is more than 2 millimeter. Therefore, you get very, very poor welding done. Up to 1 millimeter, you can get very good quality of welding done. So because of that, usually you do the welding by creating dry conditions, either by putting a water curtain and then high pressure gas jet, and then you can do the power filler wire, etc., in order to do the welding in high thick material, and you can do the welding under water. So this has been used in nuclear industry, as I mentioned earlier, and here they have tried to do the cladding by wire deposition as well as by wire-fed welding of thick material up to 10 millimeter thick material by making V groove and then realizing the welding done. Okay. Now there is another applications where people are trying to see the effect of water, paint removal. Now in aerospace industry, after large number of takeoff and landing, one needs to check the body, important part of the jet or aircraft, whether there is any fatigue cracks has grown. Now, these fatigue cracks may not be, micro cracks may not be seen in presence of paint on the surface. So after certain time, certain number of taking off and landing, all the jet plane and aircraft, those are called in the hangar, and there the paint on the surface needs to be removed without damaging the metal surface. And here the laser beam is being used to remove the material. Now, many a times it has been seen in some of the material when you try to use in air or gas jet, there is a lot of burnt ashes of the paint that remains there. Okay, that needs additional mechanical means to remove these ashes. But when you use the water-assisted paint removal, then you don't need any secondary process to remove the ashes, and you can get very good quality of paint removal without damaging the surface beneath. Okay. Now, other applications which is very important, which is being done, is a laser shock pinning, where you have got, this is similar to conventional short pinning in order to introduce certain compressive stress to improve the fatigue life of the component. So here you have got the workpiece. On that you put a absorbing coating of black paint or black tape, in which the laser beam is going to get absorbed and form the plasma. And this is also going to protect the workpiece surface. On that, you put a water layer, which is of the order of around 2 to 3 millimeter. Now, when the laser beam is incident, the laser power density is controlled in such a way that it is not absorbed in water, and that limits is around 6 gigawatt per centimeter square. So if your power density is below 6 gigawatt per centimeter square, then it is directly passed through the water and then is going to incident on the coating. And this coating, black coating, can readily absorb this laser power, and therefore it is going to get heated up, form the fume and plasma, and this plasma will try to expand, and this is going to generate a lot of pressure. Now, this expansion is going to be confined or restricted by this water layer. Therefore, in comparison to in air, in water, it is going to generate 4 times more shock wave or pressure, plasma pressure. And this pressure is now going to propagate inside the material, and this material, when it increases this compressive stress, increases the dynamic yield strength of the material, then it can cause the plastic deformation, and through that introduce a good amount of compressive stress. So recently, we have tried to improve the fatigue life of the electron beam welded titanium welding by laser shock pinning. And if you can see that when the after the welding by the electron beam on the surface, when you test, you get the tensile stress. But when you do the laser shock pinning, you get the compressive stress. With this, you find that the yield strength has increased, fatigue life has increased, hardness of the fusion zone and heat affected zone has also increased. And as I was trying to discuss with Professor Boschak, that here one of the reasons for improvement is that twin formation, which we find because of the laser shock pinning. And at the end, there is another interesting applications of the laser underwater is the laser ablation is water to generate nanoparticles. Now the gold nanoparticles and silver nanoparticles are being generated with nanosecond and femtosecond laser pulse irradiated in aqueous solution. So if you see that this is the aqueous solutions, it could be deionized water, and then the laser beam is incident focused laser beam, and here the material is ablated, and in this assisted by water cooling, it generates lot of nanoparticles in the range. So nanoparticles generated in aqueous solution, deionized water is in the range of around 25 microns. So from 15 micron to 30, no, nanometer, 15 to 30 nanometer particles have been generated by this process. And this is one of the very interesting method to generate nanoparticle of very uniform size. So here, in order to see that how this liquid transmission that reduces because of the nanoparticle, and here the color, how it gets changed because of that. Okay. So with this, we reach to the end of my talk. So what we discussed is the high power laser beam, especially Nd:YAG laser, fiber laser, diode laser, can be directly taken underwater, transported through low optical fiber to do lot of processing. All laser material processing modalities can be done underwater by either creating dry conditions or assisted by water jet, and you can get advantage of water because of its high shear strength compared to the air jet, higher cooling effect compared to the gas or air jet, and also the confinement of the plasma pressure inside the water. So all these effects can be exploited in order to realize better material processing with the assisted with the water or underwater. I'd like to acknowledge my colleagues who had some of whose results I presented. Yuvraj, who is now assistant professor at IIT Indore, Dr. Malik, he is professor at IIT, assistant professor IIT Bhubaneswar. Dr. Sagar Sarkar, he is working as a senior scientist with me presently, and my research colleague, student, PhD student, Anshuman Chattopadhyay. And now at the end, I would like to thank you for your very kind and patient attention. Thank you to all of you. And I may add that as some of you may be interested, I will share the PDF file of my talk, as well as if there is any questions, you can ask. Otherwise, you can share the question. I will try to respond later on also. So I will be available. Thank you very much.
Thank you, sir. Participant, is there any question?
This is Dr. Yeah.
Yes, sir. You can ask.
Sir, I have one question. You mentioned that you observe twinning through short pinning. What was the typical size of those twin plates, and what was the operating temperature?
Operating temperature is the room temperature, because the laser plasma and everything is forming on the surface. The material is not getting heated up.
And you said the material. What was the material used?
In this case, we had the titanium we showed. We have also seen in 304 stainless steel as well.
Okay, this titanium is pure titanium, right?
Commercial grade titanium.
Okay.
Titanium grade 2. Yeah.
Okay, so this looks like this is deformation twin rather than.
Yeah.
Okay.
Okay, sir.
Hello.
Hello.
Yes, ma'am. Yes, ma'am.
Thank you, sir.
I have a
Thank
question.
you. Oh, okay, Dheeraj, then you can ask.
Sir, my name is Dheeraj Narayane. I have a question. Sir,
Yes, go ahead.
Is it possible to perform laser shock pinning on thin films up to 100 micron?
100 micron, these are thin film. If
Yes.
these are standalone, then instead of shock pinning, what we'll going to get is the deformation. Okay, because there will be a lot of
Yes.
mechanical pressure, so it will get deformed. But if it is backed by a solid surface, then one can try to see. Yes.
Sir, in
Yeah.
future, if I want to perform this, sir, can I contact you and use your expertise to
Yes,
perform?
yes. You can regularly use our laser facility. You can write only after the lockdown is removed. Okay. Yes, yes. You are welcome to use.
Okay, sir. Okay. Thank you.
We will be happy to extend the facility. Yeah. Yes.
Okay, sir. Thank you.
Okay, sir. Any more question from participant? Okay, I think everyone is hungry. That's why.
Yes, yes, yes. Yeah, yeah. They can
Thank you,
share
sir,
the
for-
questions to me. I can share my email. You can share my email to all the participants who are interested, and I will share the slides PPT PDF file with you to share with your participants. Okay.
Okay.
Thank you, sir. Okay, sir. Sir, I am Dr. Mutunja Rao.
Yeah. Hello.
Sir. Hello, sir.
Good
Sir,
noon.
thank you very much for accepting our invitation.
It was my
Both you
pleasure.
and Anup, sir. And we are very much grateful to you and Anup, sir, for spending time with us.
Welcome.
Well, thank you. Thank you.
Okay. Then I am just now logging off. Then. Yeah.
Okay. Okay.
Okay.
Okay, sir.
So, Ankush?
Sir.
Yeah. Now we'll we'll close the meeting.
Okay, sir.
Yes, sir. Yes, sir.
Have you
I've
shared
shared the
the
form.
feedback link?
Yes, I have shared the form and it just started to come in.
There is an announcement that we are providing this feedback link in order to get the feedback, but we will concentrate on 70% attendance, and that is mandatory to get the certificate. So this feedback link we can ignore, but the percentage of attendance, that is very, very important, and we will stick to that issuing the certificates. Okay, thank you very much. Tomorrow again we will join at 10 a.m. with other experts. So thank you everybody for joining with us.
Thank you, sir.
Ankur, now you can close the meeting.
Okay, sir. Thank you, sir.